So I have mentioned previously about how strong an acid or a weak acid or whatever. And so we need to be able to figure out what we mean by that. And so basically a strong acid is something that when you put it in water, it's going to turn into 100% ions. When you split apart a covalent molecule or an ionic compound into ions, you're going to call that dissociation. So dissociation. If it's 100% dissociation, that is, it completely turns into the component ions, and that's going to be demonstrated by your arrow going one way, then that means that the reaction is going to go that way. It's favored to the right, we call it. And so it's going to be, we've already learned, a strong electrolyte and strongly dissociated. And you can tell this if you add water and acid together very quickly. Sometimes they will heat up, and so it can be a very vigorous reaction. And so some of the strong acids are hydroiodic acid, hydrogen bromide or hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid. Notice what's missing from the halide group is HF, because HF is weak. When a weak acid dissolves in water, only a very small amount is going to dissociate. And so since we have this situation where you maintain some of this form, you don't 100% dissociate into the component ions, we are going to have an arrow going both ways. Notice though, since not much or very little is made, then our arrow going to the right is a bit smaller than ours going to the left. And that's one way that we can communicate that it's favored to the left, which means that more of this is going to remain than it's going to break apart into the ions. And so common weak acids are phosphoric, hydrofluoric, carbonic, and hydrocyanic acid. So trying to show you where HCl, which is a strong acid, is completely dissociated, whereas acetic acid dissociates somewhat, but most of it remains in the molecular form. Okay, and so that's why these are weak electrolytes rather than the strong electrolytes that we see in a strong acid. When a strong base dissolves in the water, same thing. 100% of that base is going to dissociate. So this will be gone, and it will all turn into the sodium ion and the hydroxide ion. Commonly sodium hydroxide, potassium hydroxide, anything in group 1A is going to typically be a strong acid. When a weak base, strong base, sodium hydroxide, potassium hydroxide, strong base, because they dissociate 100%. When a weak base dissolves in water, the small fraction again is going to dissociate, so most of it's going to remain as ammonia. And ammonia is like the poster child for a weak base. Ammonia is our go-to weak base. It does dissociate somewhat into ammonium ion and hydroxide ion, but the majority of it is going to remain in the molecular form, which is your NH3. So your strong base, again, completely dissociating like we saw in the acid, and your weak base mostly undissociated in the form of ammonia in this example. So a strong acid readily donates a proton, and so if you have a strong acid, your conjugate base is going to be weak. And if you have a strong base, then your conjugate acid is going to be weak. And the reverse is also true. if you have a, if you have a weak acid, your conjugate base is going to be strong. If you have a weak base, then your conjugate acid will be strong. So this is just a table that kind of shows you about strength relative to other things. So notice that as the strength of the acid is increasing, the strength of the conjugate base is decreasing. And that's because if you think about what's going on with this, and we'll just use hydrochloric, for example. Sorry, I'm making you dizzy. Hydrochloric acid, for example. So if I take hydrochloric acid plus water, and I'm going to 100% dissociate that, so because that's a strong acid, I'm going to produce H3O plus and Cl minus. Okay, so this is my acid. So whatever is missing the H becomes my conjugate base. So this is my conjugate base. And this is a strong acid. And this is my base, which is going to then turn into a conjugate acid. Now, when I'm saying that this is a strong, and so this goes this way 100%, that means that my chloride, which is my conjugate base, is so weak that it can't reform the hydrochloric acid. So that's why it completely stays in this form. If I have a weak acid, like acetic acid, okay, so it's weak this time, and it does not, or if you recall, much less than 100%, okay, so I'm going to get H3O plus CH3OO minus, the acetate ion. This is my weak acid. If I have a weak acid, I'm going to have a strong conjugate base. What is the definition of a base? It is going to accept hydrogen, right? So it's going to be accepting hydrogen and then reforming the acid. So because, you know, it's going back and forth, back and forth. And so since this is a strong conjugate base, it's going to favor the reaction of going back. And so you're going to be reforming this acetic acid faster than you are forming acetate ion. And so that's why most of what you have in the solution is going to be in the molecular form.